Let's try to visualize what's happening in part 3 here. We might have some sequence that takes values that go back and forth and back and forth. Maybe it's an alternating sequence or a sine n type sequence or something. It takes some values going back and forth. The Limsup will be somewhere up here, right? It will be a frequently visited value or a value to which the many terms get very close. But what if we take a value greater than that? Well, some of the early terms of the sequence might actually exceed that value. But not very many terms of the sequence will exceed that value. And what 3 is really telling us is that only finitely many of the terms can exceed a value which itself is bigger than the Limsup. So that's the point of number 3. Let's see if we can prove this. So what we're going to do here in 3 is we're going to assume that we have a value greater than the Limsup, and then, well, we're going to see what happens. So let's let the Limsup of an be s. And let's assume that x is greater than s. So if the Limsup of an is equal to s, then what does that mean? That means that the limit as n goes to infinity of the supremum of an, where n exceeds cap n, is equal to s. And that s is less than x. Okay? So we've got this thing, which may be very, very complicated, but it's a function of cap n. And the limit of this thing, this is a sequence which depends upon cap n, and the limit of this thing is equal to s, which is less than x. Well, if the limit of a sequence is equal to s, and s is less than x, then eventually one of the terms will be less than x. So for some cap n, then what do we have? We have one of the terms of this sequence will be less than x. So we will get one of these things. It won't necessarily be equal to s. None of the terms have to equal s, but one of the terms will certainly be less than x. And what does this mean? That means that for some n, this tail sequence has a supremum which itself is less than x. Now, if the supremum of a set is less than x, then all of the members of the set are less than x. That is, well, then, I shouldn't say i.e. because it's not logically equivalent. So then for all n greater than n, an is less than x. And so how many, so that's all of them greater than some cap n. How many of them could actually exceed x or be equal to x? Only finitely many. So thus, for all but finitely many n, then we get an is less than x, because this is only, there are only finitely many exceptions here, those up to and including cap n. So that proves that if the Limsup is less than some value x, then eventually the sequence will get below the value of x and forevermore stay below the value of x. Only finitely many terms could be equal to x or exceed x. And so that gives us this property here. Now let's compare 4. 4 describes what happens when we have an x value which is less than the Limsup. Then what we expect is we expect many terms of the sequence to eventually exceed x. Now, we don't necessarily know that all but finitely many of those terms will exceed x. Because if the sequence itself doesn't converge or alternates between two values or something, then, you know, we could have infinitely many terms less than x, and then we could have infinitely many terms somehow getting closer to the Limsup. So we can't necessarily conclude here that all but finitely many of the terms are greater than x, but we can conclude that infinitely many of the terms are greater than x, okay? So that's what we're gonna prove next. We're gonna assume that we have a value less than the Limsup, and we're gonna prove that infinitely many terms get greater than that value. So assume x is less than s, which is equal to the Limsup of an, well, the Limsup of an, which is equal, of course, by definition, to the limit as n goes to infinity of the supremum of the tail. Now, by presumption, this limit, which depends upon cap n, exists. Now, let's look closely at the terms here, which are a function of cap n, and see how they relate to each other. So notice here that the tails are related to each other. The supremum of the tail for n is greater than n, is related to the supremum of the tail where n is greater than n plus 1. So I want to look at the term n in this sequence and term n plus 1 in this sequence, and I want to say that there's some relationship between them. Now, ignore the supremum for a moment. If we ignore the supremum, then this is simply a set, and this is also a set. And the sets are related because this tail set is a subset of that. Now, if this is a subset of that, then the supremum for this set must be less than or equal to the supremum of that set, because a supremum of a subset is going to be less than or equal to the supremum of the superset. So any upper bound for this set will actually be an upper bound for this set. And so the least upper bound for this set can't be any larger than the least upper bound for that set. So, so we get a relationship between these suprema, which means that as a function of cap n, the limit being described here, well, the sequence being described here is a decreasing function of cap n. So the sequence as a function of cap n, supremum an n greater than n, so think of this as something that depends on cap n, decreases with cap n. That is, the larger cap n is, the less of the tail we're getting, and the smaller the supremum may be. Now, its limit is equal to s, which is still greater than x. So its limit is s, which is greater than x. So what we have here is a monotone decreasing sequence whose limit is s. If it's monotone decreasing and it approaches s, and s is greater than x, then every single term in this sequence must be greater than x. So what that means is x is actually less than every one of these things. So in other words, the least upper bound of this set is always greater than x. Now, okay, what can we make of that? Well, if the least upper bound of this set is greater than x, then that means that x itself is not an upper bound. So x is not an upper bound for the set an n greater than n. And this is true no matter what cap n is. So that means that some element of this set has to exceed x. So for any cap n, some an with, so some an is greater than x for some n greater than cap n. Okay, so what does this mean in practical terms? What we've deduced here is that no matter where you start the tail of that sequence, somewhere in that tail you'll get a term which exceeds x. But if you can cut off the tail anywhere and find a term which exceeds x, then there must be, then you could read out to that term and cut it off there and then find another one, and then you could read out to there and cut it off and find another one. There must be infinitely many terms that exceed x. So an is greater than x for infinitely many n is the right conclusion here, and that's what we were trying to show. If x is less than the Limsup, then x is less than infinitely many of the terms. So infinitely many of the terms will be greater than x. It's not necessarily true that infinitely many of the terms will be greater than the Limsup. It's not even true that infinitely many of the terms will be greater than or equal to the Limsup. But if we back off, if we take a number slightly less than the Limsup, then it is true that infinitely many of the terms will exceed that value. And so this is a convenient, so this is kind of complicated because it doesn't describe the Limsup, it describes numbers less than the Limsup. And this one similarly doesn't describe the Limsup, it describes numbers greater than the Limsup. But at least it has the advantage that it describes the relationship with the sequence terms themselves instead of a tail and a supremum and a limit of that. So finally, let's go back to 2. In 2, we proved that if the Liminf of a sequence was equal to the Limsup of that same sequence, and they were both equal to a, then that limit of that sequence must exist and must also be equal to a. And 5 is the converse of 2. If the limit exists, then the liminf is equal to that value and the limsup is equal to that value. Let's prove 5 next. So what we're going to do is we're going to leverage what we know from 3 and 4. It can be proven directly based on the definitions too. That's also an option. So for 5, we're going to assume that the limit as n goes to infinity of an is equal to a. And the goal is to show that if the limit exists, then it must be equal to the liminf and the limsup. You might say, well, then what's the point of the liminf and the limsup? The point of the liminf and the limsup generally is to analyze sequences for which the limit doesn't exist, and then still reason about them. Like an alternating sequence that goes -1, 1, -1, 1, we can still reason about, well, there's sort of an upper limit and there's also a lower limit. And so like normally we don't have to worry about liminfs and limsups when the limit exists, but this is what happens when it does exist. So we're going to assume that the limit is a. So what does that mean? That means, so let's let epsilon be greater than 0 and say what that means. Then that means for any n, there exists a cap n in the naturals. For any n, sorry, I'm getting the limit. I'm getting myself confused. So then there is some cap n, so that for any natural number little n, if little n exceeds cap n, then an minus a is less than epsilon. And as usual, this is the same as saying that an is greater than a minus epsilon and less than a plus epsilon. Now, notice that this finds infinitely many terms between a minus epsilon and a plus epsilon, namely all of those terms for which the index exceeds cap n. Not only are there infinitely many terms between a minus epsilon and a plus epsilon, but there are also, which is to say more, all but finitely many of the terms lie between a minus epsilon and a plus epsilon. Because the only terms that might not, if this was true, were the terms at position cap n or earlier. And so we have not only infinitely many terms in this range, but also we have all but finitely many terms in this range. Let's compare the limsup to both of these values in light of what we know from 3 and from 4. So let's let S be the limsup of an. Now, if the limsup is less than this value, then we're going to have a problem because we have infinitely many terms greater than that value. So if S is less than a minus epsilon, then this contradicts, this is going to contradict part 3. So let's say what part 3 would tell us. If S is less than a minus epsilon, then an is going to be less than a minus epsilon for all but finitely many n. This is clearly not what's happening because we have all but finitely many actually in between a minus epsilon and a plus epsilon. And so that's not happening. So what we should conclude here is thus S is greater than or equal to a minus epsilon. So if S is greater than a plus epsilon, if it's too far on the other side, then what can we conclude from 4? We can conclude that, that a plus epsilon is going to be less than an for infinitely many n. And that's also a contradiction because it's not. I mean, all but finitely many of the n's are in between here. There can't be infinitely many greater than a plus epsilon. And that says that S is going to be somewhere between a minus epsilon and a plus epsilon. But a is a fixed value, and s is also a fixed value. And this is true for all epsilon. The only way s can be so close to a for every epsilon is that s is equal to a. So if we use the corresponding statements for liminfs, that is the statements corresponding to 3 and 4 for liminfs, then we can prove also that the liminf of this sequence is also equal to a. So we've proven that the limsup is equal to a, and similarly for the liminf. So similarly liminf. So that establishes, well, half of this, and then the other half is similar. So if the limit is equal to a value, then the liminf and the limsup agree and are both equal to that same value. Also, on the basis of 3 and 4 and their corresponding statements for liminfs, we can prove this statement in 6, which tells us about the relationship between the liminf and limsup and what happens when you take the liminf or the limsup of a subsequence, which is important to know. So here, the idea here is that we have a sequence and it has its own liminf and limsup, and then we take a subsequence, and the subsequence can have a liminf and limsup. And what we are concluding here is basically that the subsequence liminf and limsup are going to be less extreme, or at least no more extreme, than the original sequence liminf and limsup. So the liminf and limsup of the original sequence go on the outside, and then the liminf and limsup of the subsequence are going to be, well, they're also going to have this relationship that their liminf and limsup are going to be related in that way, but they can't be more extreme. Basically, the limsup of a subsequence can't exceed the limsup of the original sequence itself. So they're going to be sort of less extreme, at least not more extreme, than the liminf and limsup of the original sequence here. So we're going to prove this on the basis of 3, and I'm only going to focus, so 6, so we'll prove, it's going to be similar for limit, but we're only going to prove under these conditions that the limsup of the sequence Bn is less than or equal to the limsup of the sequence An. For liminfs, it's basically the same game. And for this central inequality here, that's basically just a restatement of part 1, which we've already proven. So I'm only going to focus on the proof of this statement here. And what we're going to do is we're going to say, well, let's suppose, for the sake of argument, that the inequality were the other way, and then we're going to see what happens. So suppose for contradiction, what are we supposing? We're supposing that the limsup of An is strictly less than the limsup of Bn. Now, if the limsup of An is less than the limsup of Bn, then we can place a value in between them. So let x be a number between. So in other words, limsup An is less than x, which is less than the limsup of Bn. Now, x is then greater than the limsup of An, and so part 3 applies. So that means that An is going to be less than x for all but finitely many of the terms n. So except possibly for a few finitely many, An will be less than x because x is greater than the limsup of the An. Okay, what can we make of that? Well, here, by assumption, Bn is a subsequence of An. Anything true for all the terms of the sequence An is going to be true for all the terms of the sequence Bn because it's a subsequence. Anything true for all but finitely many of the terms of An will be true for all except possibly finitely many of the terms of Bn because it's a subsequence. And so if this is true for all but finitely many of the An terms, then it is also likewise true for all but finitely many of the Bn terms. So Bn is also going to be less than x for all but finitely many n. But wait a minute, x is less than the limsup of the Bn's, and so we also can invoke 4 on the relationship between x and now the sequence Bn. So also by 4, So what do we get? We get x is less than bn for infinitely many n. And you see, that's impossible, right? For all but finitely many, we get bn smaller. And then for infinitely many, we get bn bigger. And so that's a contradiction. So it's a contradiction to what? It's a contradiction to this thing that we assumed for contradiction. And so we get thus the other inequality is correct. Limsup bn is less than or equal to limsup an. Now, I'm not going to prove this for liminfs. So basically, there's a version of 3 and a version of 4 for liminfs, which we would get to prove this thing, and it would be basically the same thing. So if you know, for example, that you have a sequence and the liminf is 1 and the limsup is 10, and then you take a subsequence, it might have a liminf of 2 and a limsup of 9, for example. Or they might both be equal to 5, or they might be something else. Any subsequence will have liminf and limsup, which is less extreme. This applies to, well, what happens if the subsequence itself has a limit? We've said that if, we've said in 5, that if the subsequence itself has a limit, then it must be equal to the limsup and the liminf. So any subsequential limit must be a value of a subsequence, which must be, these two terms would then be equal, and then they would still have to be in between the liminf and the limsup. And that gives us 7, which basically, we'll write something out a little bit, but that's basically it. So any subsequential limit must lie between the liminf and the limsup. So to prove it, let's see, let's let Bn be a subsequence. So a subsequence with limit of Bn equals L. So then liminf of Bn is equal to L, which is equal to the limsup of Bn. And we furthermore know that the liminf of An is less than or equal to the limsup, liminf of Bn, which is less than or equal to the limsup of Bn, which is less than or equal to the limsup of An, and everything in the middle is L. And so that proves that if you have any subsequential limit at all, then it must be between the liminf and the limsup. And this is more evidence that the liminf is really the lower limit among all subsequential limits, and the limsup is really the upper threshold among all subsequential limits. No subsequential limit can be greater than the limsup, nor can it be less than the liminf. There is one last piece of the puzzle before we say definitively that the limsups and the liminfs describe the subsequential limits. And that is, we need to know that they are actually subsequential limits, that the liminf is always a limit of some subsequence, and that the limsup is always a limit of some different subsequence. So, so that's what we're going to do next, and that's what's stated there in 8. Here we go. So, so we're just, as usual, we're going to do this for the limsup. So let's let S be the limsup of An. Now, we're going to try to show that we have some subsequence of An that has a limit which is equal to S. So what we're going to do is we're going to say, well, let's choose an epsilon, although I haven't quite clarified what it's for. We're not proving that a certain limit is equal to a certain value yet, but we're going to choose an epsilon. And then we're going to create a range. So consider the range, which I should call an interval. Consider the interval S minus epsilon, S plus epsilon. Now, S minus epsilon is less than S, and S plus epsilon is greater than S, and so parts 3 and 4 apply to them. So let's let's say what we can learn about s minus epsilon and s plus epsilon on the grounds of the assertions of 3 and 4. So, so s minus epsilon is less than s. So basically, we're going to use it as the x in part 4 to conclude so that there are infinitely many values. So s minus epsilon is less than an for infinitely many n. All right, that's what 4 tells us about this value x equals s minus epsilon. Now, s plus epsilon is greater than s. So if we set x equal to that, then that means, so what do we conclude from that? An is less than s plus epsilon for all but finitely many n. Okay, now I'd like to put these conditions together, but it's a little bit subtle to put these together because one of them is true for some little n, and the other one is true for some little n, and it's not clear whether there might be some overlap that either the conditions would be true for all little n or for some little n or what, right? If you have a condition that's true for some and another condition that's true for some, there may be none for which both conditions are true. But in our case, there must be infinitely many for which both conditions are true. This condition is true for infinitely many n. And among the infinitely many n for which this condition is true, there are only finitely many exceptions to this condition. And so, in fact, both of these conditions will be satisfied for infinitely many n. Maybe not the same n here, right? But a subset of them by taking away the at most finitely many for which this condition fails. And so what we can conclude from this is that we get an within this range from s minus epsilon to s plus epsilon. We get this for infinitely many n. Okay. Now what we're trying to do is we're trying to produce a subsequential limit to be equal to s. We're not trying to show that the limit of an is equal to s. That might not be true. We're trying to show that there is some subsequence. So what we're going to do now is we're going to generate the subsequence. So I'm going to let a1, well, let's choose. I'm going to choose a1, a sub n sub 1, so that s minus 1 is less than a sub n sub 1 is less than s plus 1. Basically, I'm saying this argument works for any epsilon, so it works for 1, so I can do this for 1. I'm basically saying, okay, in what we reasoned about above, let epsilon be 1, and then there must be, since this must be true for infinitely many n, I'm just going to pick 1. All right, pick 1 for which this value is between s minus 1 and s plus 1. Now, that's all well and good. What are we going to pick next? The next one, we're going to pick so that a sub n sub 2 is going to be like somewhat more tightly bound close to s. That is between s minus a half and s plus a half. Now, can I do this as well? Sure, because I can plug in epsilon equals a half here, and I know that there are infinitely many n for which an is in this range, and I can pick one. It's not enough to pick one, though, if I'm trying to make a subsequence. If you remember, a subsequence has to be given in increasing order. And so it's not enough to just pick one. I need to pick one so that n2 is greater than n1. And n2 exceeds n1. Do I know that I can get one for which n2 exceeds n1? Sure, because, I mean, being less than or equal to n1, that only eliminates finitely many problems. And I know that this is true for infinitely many n. Infinitely many n will have an somewhere in this range. So I can read out beyond n1 and still be sure that I will find one. And then we're going to continue in this way, a sub n sub 3, so that s minus a third less than a sub n sub 3 less than s plus a third. And of course, I'm going to furthermore require that n sub 3 be greater than n sub 2 so that that n sub 3 index will be farther on down the list. And then I'm going to continue choosing this way. And I can always continue choosing this way. There will never be any problem because every choice has been guaranteed that it has infinitely many n for which it's true. And after a certain collection of choices, there will always be available choices for the next sequence term so that the next one will be true. And I'm going to continue changing epsilon, so it's 1, a half, a third, a quarter, a fifth, etc. So this produces a subsequence, so we get a subsequence a sub n sub k, and each one is sort of getting closer and closer to s. So basically we apply the squeeze theorem using s minus 1 over k is less than or equal to a sub n sub k is less than or equal to s plus 1 over k. This term converges to s, this term converges to s, and this thing, therefore, converges to s by the squeeze theorem. And so what did we do? We produced a subsequence a sub n sub k, which converges to s, and we demonstrated that the Limsup of the sequence an is equal to some subsequence's limit. In other words, the Limsup is one of the subsequential limits. So all of the subsequential limits lie between the Liminf and the Limsup, and the Limsup is one of the subsequential limits as well. And you give a similar proof and you show that the Liminf is also equal to one of the subsequential limits. So this demonstrates that the Limsup and Liminf are among the subsequential limits and that all the subsequential limits are bounded between them. And that gives a pretty strong indication of why we call this kind of the uppermost subsequential limit and the lowermost subsequential limit.